I'm somebody who prefers the carrot to the stick. I don't want to have a lot of regulations to somehow force us into a different lifestyle. I want to have ways to draw people into a better life. And some of what you see around you here at Collect Jordan is really a prime example of the carrot. This is how we all could live a little better with a little bit of design, a little bit of development. So let's get into it. Some of the science that we've had come to us over the last 100 years or so is all coming to this similar kinds of agreements. You don't find a lot of disputes about most of this stuff. We're past our threshold for carrying capacity on the planet, and you can see it in lots of different ways. We have resource drawdowns. Things are becoming more scarce. We have crises form in all of these different areas, not just climate change, but ocean acidification, loss of biodiversity, global fresh water, the nitrogen cycle, the phosphorus cycle. All of these things are approaching crisis dimensions. And so doing nothing is not an option. We have to start to think about what are the real serious options that we have. But we're tipping towards the unknown. We're engaged in a high-stakes game, unwittingly crossing boundaries, and don't have any historic or geologic example of having crossed these boundaries before. And so we're off into a new world. We've passed the safe operating space. This is the way I was taught the Earth's habitable zone when I was in school. It's this Goldilocks zone where it's not too hot, not too cold, just the right distance from the sun. That Earth is in this nice, comfortable, habitable zone. And so for many decades, this is the way science was taught. But this is a really scary thing because we only just discovered in March 2014, astronomers came back with a new piece of information. Earth is actually at the inner edge of the habitable zone. We're in 99% of the habitable zone is outside of our orbit to the sun. We're on the 1% inner edge of the habitable orbit of the sun. A slight variation would tip us into uninhabitability. And yet, what are we doing? We're doing everything we can to make Earth uninhabitable. This is our global warming carbon concentration chart. Most of you have seen this. It goes back 400,000 years. Well, most people who study human evolution place Homo sapiens at somewhere around 200,000 years ago. The newest evidence puts it back around 350,000 years ago. There's some evidence that you had tribes of upright, wandering hominids in southern France with shelters, seasonal shelters that are still there, Terra Amata, along the coast at 400,000 years ago. But we really don't have any indication whatsoever that humans have ever been on a planet that had greater than 300 parts per million of carbon in the atmosphere. We've always kept our temperature within a comfortable band there, and our carbon concentrations, which are the indicators of the temperature, in that comfortable band. And where are we today? Top of the chart. Actually, we're at the middle of the chart, and we're headed to the top of the chart. So we're outside of the known universe. We're outside of human experience, going back through evolution. We're already outside of that. Now, the full effect is yet to take place, but we're starting to see it. You look around, sea levels rising, superstorms, and you can predict the future a little bit. This might be what Kinsale looks like in not too distant future. You can think also in terms of what happens if the Atlantic current begins to slow down because of the fresh water at the poles and because of the change of temperature of the ocean. And you get into Ice Storm Ireland. which could happen in summer months because of the change of the warming that normally comes from the Caribbean to make this a maritime climate. And so you start to see all of Northern Europe experience these sudden cold snaps related to this shift in change. So a lot of what we've been seeing, I can go back 20, 30 years and look at the literature, look at the advertising, look at the different environmental groups, and we see these prescriptions. To me, these have always seemed a little lame. Change your light bulbs, buy an electric car. It's a bigger problem than that. It's a bigger problem than that. And those kinds of small changes in lifestyle really won't cut the mustard. If we're looking at where we are already on the changing of the greenhouse gases, where we exist at the edge of the habitable zone, most of the science that if you go to the scientific conferences, like if you went to Marrakesh last year, this chart came up a bit. This was the scientists from the IPCC and the Met Office and the Tyndall Center and so on, all looking at the emissions reductions that are proposed under the Paris Agreement, previously proposed under Kyoto. And what they've done is they said, okay, if we're really smart and we started to cut our emissions around 2010, we could have come down at a nice 2% slope, which is about the same slope of increase that we experienced over the last 2 centuries as we got into fossil fuels in the first place. We gradually grew the economy and the consumption of fossil fuels at about a 2% annual rate. We could come down at the same rate if we'd started in 2010, but we didn't. If we start in 2015, we can come down at a 3.6% rate, but we didn't. So we can look at 2020 now, and it's about a 6% rate. Chances of us starting to come down in 3 years, pretty slim. The pledges are not there. The farther you go, the steeper the curve down has to be, and you actually have to get into what they now call negative emissions, or decarbonization, where you're taking carbon out of the atmosphere. It's assuming that emissions are going to continue, that we're still putting carbon into the atmosphere for so long that the only way out of this is to find ways to take the legacy carbon out of the atmosphere and to start pulling it out eventually. And that takes you down below zero. Well, if you know about the exponential function, let's say the curve down is 7%. That makes it easy for mathematical purposes. Something that's increasing at 7% is doubling every 10 years. Something that's decreasing at 7% per year is getting half every 10 years. So if we have to bring civilization energy consumption down at a 7% per year rate, which is what the chart says, then we're talking about half the number of cars on the road in 10 years. Half the amount of fossil fuels consumed in the next 10 years. Half the asphalt put into highways, or new buildings being built, or steel production, or any of the indicia of industrial civilization. And then, 10 years after that, half again, to a quarter of what we have now. And 10 years after that, half again, to an eighth of what we have now. It keeps going like that. Is that even conceivable? Is that even possible? Can you imagine a decline rate like that for civilization, given our history, given our natural inclination towards growth? And so naturally, no politicians are embracing that. That's not a slogan that anybody's saying, half in 10 years. You won't find that on any slogans. And so it puts us again in this dilemma. This is the chart that they came up with the Club of Rome back in 1972, the Limits to Growth study. And the climate problem doesn't exist in isolation. With or without a financial collapse, which is now overdue. We've got other tipping points: less available food, water, more diseases, famines, migrations. That's not happening 20 years from now. That's happening now. That's the point that they said in 1972. We start to see these crossing of the curves. And exactly that's the case. And population is a big driver of all that. We're on a finite world. We have limited resources. And what they said in 1972 was there's limits to growth. And we're going to experience limits to growth, whether we experience them in an intentional way of initiating measures to slow and then degrow, or whether we experience them in a haphazard way where it becomes a crisis. Well, if you take the greenhouse gases already up in the atmosphere, if those were fully expressing their equilibrium effect, we would already be 6 degrees warmer, seas would already be 7 meters higher, and we would already be at ice ship Ireland for the slowing of the Atlantic. But we haven't got to that, and it's because these moderating effects of the oceans are so enormous. The moderating effects of the heat absorption by land masses, that it takes a while, it takes decades for that stuff to set in, possibly even centuries. We can't really predict too much about the timing because we're out of the known world. I went to the Paris conference, and afterwards I wrote this book called The Paris Agreement. And Paris was a landmark, but it took more than 20 years to reach that deal, and it fell short of actually bringing us back from the brink. If all the pledges made at Paris were kept, we'd still be at more than 3 degrees increase later this century. And as we saw from that chart I showed earlier, 3 degrees. We don't know the threshold for human extinction. We're already out of the known history of human evolution. But we do know our species has never existed in a world that hot before. So when the world finally came together and to pledge the end of fossil fuels in our lifetime, it was a major step. They did the first thing that most governments do when they don't know what to do, is they throw money at the problem and hope that it goes away. And I call that in my book trillionization. It's the idea of realizing that your fossil fuel investments are now stranded and that you're going to lose money if you keep them there. So you start to throw money at renewables. You start to throw money at electric cars. You start to figure out how you can reinvest in other things than fossil fuels and fossil fuel infrastructure. And the problem is that when you make those kinds of investments very hastily without having done all of the work that's necessary to predict what will happen over the long term, you're re-stranding your investment. You're just taking it from one stranded investment into another one. Renewables will only take us so far, and they're based on non-renewable sources to get your renewable energy for the most part. There's a non-renewable infrastructure that underlies renewable energy. And that, by and large, comes from fossil fuels. So you can look at some of the darlings of the new investment world, and those are things like BECCS, which is Biomass Energy Carbon Capture and Storage, BECCS. And fine, it makes some sense, but what they're talking about with carbon capture and storage is gathering the flue gas from burning biomass and then injecting it in the ocean, okay, as if the coral reefs weren't already melting, as if the ocean weren't already acidified. Or maybe they'll inject it into reservoirs deep underground. Fine, except the average right now for this work, for the prototype studies that have been done, is around a 10% leakage rate. Well, in 10 years, what you put in the first year is back in the atmosphere. What kind of solution is that? Plus the energy required to take the carbon and stick it in the ground or stick it in the ocean is so enormous that it doubles, triples, quadruples the price of energy, and nobody wants to do it. So those kinds of things, we're kind of throwing money around. And I just come to the point of saying, are we just stupid? Are humans doomed to extinction from sheer stupidity? Is it our fate? Is it our destiny? Is this just the end of the road? And I can find doomer porn to surf on the web. I can read Guy McPherson. I could read others who are into near-term human extinction. They're not hard to find. And I can get confirmation bias. I can have, the people that will confirm the view that we're just too stupid to keep going. But I have to pause and take a breath and say, yes, we're in denial. The scientists have been telling us the truth, and we're not listening. We've got a cultural inertia. We have all of these things going against us. But there's got to be something. And I look at the eyes of my grandchild, and I say, it's up to me to figure out something. So I keep going around and looking, and there's this old Dickens thing, Christmas Carol, where Scrooge asks the spirit whether his future is cast already or whether he might still do something, and the spirit is silent. There's no answer. I went and I took ayahuasca in the Amazon, and the spirit was silent. There was no answer. I tried talking to different people who might have ideas, but as I follow those ideas out, pretty thin. Not really sure those would work. So I'm, for 20 years I've been dwelling in this realm of the dark night of the soul, trying to find a way, and I'm continuously eliminating what ultimately turn out to be fictions. And then I happen to wander into something that might actually work. And I'm going to talk about that for most of the rest of the night. I was on a quest in the Amazon, and I found a faint ray of hope. I was at a permaculture gathering, and somebody showed me the Terra Preta do Indio, the dark earths of the Indians. And for 500 years, those had been a mystery. Now we know what caused them and what they signify, but for 500 years, nobody really understood how you could get meter-deep, dark, rich, black soils at tropical latitudes. Because there's high rainfall that washes out nutrients, there's most of the biomass, most of the nutrients are stored in the living biomass, and if something dies, the forest quickly takes it back and recycles it into living things again. There's very little stored in the soil. And yet here you had really deep, rich black soils. How could that happen? So I'm going to take you on an exercise now in designing a strategy to save the planet. I'm going to enlist you to be fellow emergency planetary technicians. And I want you to go with me while we study this. You may be as skeptical as I was that there are no easy solutions. So we're going to start by sharing the facts that I've learned so far. Wim Sombroek was a Dutch man who was on a PhD thesis that he was working with a UN sponsor, the FAO, to study the soils of the Amazon. And he was coming across all of these interesting features. Why are these soils so fertile? What are they made of? What seems to be going on here? And he had lived through the Dutch famine of 1944, the Hongerwinter, and his father had improved their garden out back of their home by taking cinders from the fireplace out and using that as fertilizer. So he's digging in these dark earths of the Amazon, and he's starting to see cinders from a fire. And it's an aha moment. Aha! The dark earths of the Amazon are man-made. They're not a natural occurrence. They're man-made. And that actually this same thing was done here as was done in Holland during the Hongerwinter, which was the cinders were put into the soil to serve as fertilizer. So the native peoples here had this practice that they knew about, that the the charcoal seemed to do something. So he started studying that. One of the things that they learned was that when you put carbon in the form of the crystalline form that comes in charcoal in the soil, it becomes a form of carbon that's not labile. It's not going back into the atmosphere and becoming plants again when it rains back down into the earth. Normal carbon follows a labile cycle, 12 to 15 years, and it decays from old plant material. It winds up in the atmosphere. It gets rained back down. It goes into next year's plants. It goes through the whole process again. When you turn it into charcoal, that stops. It becomes what's called recalcitrant carbon. And now it doesn't it doesn't oxidize, it doesn't become carbon dioxide, it doesn't become carbon monoxide, it doesn't form with hydrogen to become methane and go to the atmosphere that way. It stays in the earth as a structure. It's not a fertilizer because it's not able to be taken up by the plants. Instead, it's a structure in the soil. And it's a structure that provides air, a structure that holds water like a sponge, and also a structure that's home for microbial life. If you look at it under a microscope, you can see why. If you were a soil bacteria and you're wandering through the soil and you encounter this, you say, oh, a condo. I'm going to move in and bring on my whole family and we'll stock these cupboards and have this be my coral reef. You can look at with a bigger microscope and you see that there's pores on the walls of the pores. And then a bigger microscope and there's pores on the walls of the pores on the walls. It's fractal. It's turtles all the way down. So you have this situation here where it becomes like a coral reef under the soil rather than under the water. And it does the same thing a coral reef does. It attracts in biodiversity, soil biodiversity. And that then serves as a continuing source of fertility for the plants. In fact, it's an amazing source of fertility. We haven't named the majority of soil organisms yet, but it's like a Star Wars cafe down there. It's a huge, in a teaspoon, there's a billion these different organisms. And as soon as you put biochar, which I'm calling the charcoal that I referred to, as soon as you put that into the soil, there's an explosion of different DNA types. Within a year, you can do a soil test and find a spread of DNA of different bacteria and fungi that had not pre-existed. It's just amazing biodiversity that springs out of that. This is important in soils and in plant life because what goes on below ground is just as important, if not more so, as what goes on above ground for nutrient density, how well plants grow, how resistant they are to disease. And you can see the succession of life in the soil following the succession, or actually preceding the succession of plants above ground. So a bare ground, desert, hard-packed clay is going to have mostly bacteria. And then you get a little bit farther on, you've got the pioneer species coming in, the woody, weedy plants. And then you start to get more fungi in. And then you have a rough balance between fungi and bacteria. You get up to vegetable gardens and hedges and things like that. Low woodlands, now you've got more fungal-dominated soils. You go a little farther and you've got deep forest, and now you've got very heavily dominated fungal-dominated soils. There's a succession that occurs, and diversity occurs along with that. This is important for human nutrition because that fungal food web that's under the surface of the soil also feeds the nutrient cycle that feeds us. And within us, 99% of the DNA in your body is not yours. It's the other things living inside your body that are doing vital functions like digesting your food. And so that microbiota that live in your gut are fed by the nutrients and by the other organisms coming into your diet from the soil food web. And the richer and more diverse that is, the healthier you are. The better your food is, the better your diet is, the better it tastes from the richness of the soil food web. It's like terroir in wine. The better your terroir for growing your vegetables, the more rich it is in biodiversity, the better your food will be. So when we're making biochar, now I'm going to give you a definition here. I don't use charcoal because if you say charcoal, it might mean the stuff you buy in a hardware store to have a barbecue with, and it might have petroleum additives to make it start fast. It might have come from something not very nice, like old tires. I don't know. Who knows where the material came from? So biochar is food-grade charcoal. It's charcoal that you can probably eat. You could eat. It's charcoal that you know it's made in controlled conditions. It follows some characterizations, and it also comes from reliable production processes that are clean. So we define biochar as agriculture grade or food grade charcoal. To get it suitable for the garden, you don't put it directly from the kiln or from the fire, however it was made, directly into the garden. If fresh from a production burner, char is bone dry, and it will repel water. But if water is going to be pushed away, it's not going to be very good for biological life. Without water, even earthworms would avoid this. So what you do first is moisten it. And you can do this in your process of quenching the fire that made it. You moisten the char, and now it goes from being hydrophobic to hydrophilic. It likes water. It becomes a sponge for water. It absorbs water when it rains, and it's a slow time release when it's dry. So then it's inviting for microbes and worms and things to come in and colonize it. And the next thing we're going to do is micronize it. So we're going to take the particle size down. When you first get it out of the kiln, it looks just like the material that it was originally. If it was a piece of bamboo, it looks like black bamboo. If it was a log, it looks like a black log. But now what we're going to do is we're going to run it through a grinder. I like to use a leaf shredder chipper these days. I used to use a gunny sack in a golf cart where I put the gunny sack full of biochar down and run over it about 6 times. But now I'm just using a leaf shredder chipper, and in a few seconds I get very fine powder biochar. An area of 1 gram of biochar, about an area the size of a pencil eraser, has the surface area of this entire space here because of the surface area of all those pores. So those pores also have what's called a cation exchange capacity. And that means consider them like the walls are slightly magnetic. And if nutrients pass through in some form, they tend to stick to the walls and be there and available for transport or for feeding microorganisms. And so it has that capacity if it's properly conditioned, and micronizing it, if I take it down to about the size an earthworm can digest, that's about the right size for biochar to be. And then mineralizing means you're adding minerals so that the microbes will have good diet and have that available for the plants. And you might want to do a soil test and find what minerals your garden needs and add in those particular minerals. What I usually do to achieve all of these is to put it in the compost pile. Leave the fresh biochar in the compost. It gets moistened, it gets mineralized, and then finally it gets microbialized. So microbial inoculation. You want the bacteria to move in and live there. And if you put raw biochar straight into the garden, you're going to have the first year or so when all of those microbes are leaving the rest of the garden to go into the biochar. And they're colonizing the biochar, but they're coming away from your plants. They're not doing your plants any good, and your plants are doing poorly because of that. Most of the negative studies of biochar, and there are a number of them out there, they make headlines every now and then, are studies of raw biochar where they didn't microbialize them before they started using it in an agricultural setting. And so what did they get? Poorer results in the garden. Predictable. So what you want to do is microbialize before you start. This is how we do our microbialization.
So what we start with is basically just water. You bubble it for 24 hours to get all the chlorine out of it. And then you add micromate from Mesa Verde, which is basically humate and fulvic acids to help lock up the leftover chlorine, drop it to the bottom, and then you're ready to fill your bag and put it in the water Your bag consists of different types of soils, worm castings, bat guano. Those are the types of ingredients you want to add to the bag. Within the 24 hours of brewing process, you want at least a third of that bag to exit into the water. And then you're going to add fish hydrolysate as your micro meal, and that's going to get the fungi and the bacteria all fed and active and ready to go. And then I also sometimes add kelp. That's, if depending on your application, kelp is a good one. Feather meal if you have that available.
Feather meal, what's that, broken up feathers? I mean, ground up feathers from poultry?
I actually don't use feather meal yet. I stick with kelp, micromate, and fish hydrolysate. And those are my main ingredients. But I also use worm castings in almost every batch I do, and I use bat guano.
Have you ever used biochar?
I have used biochar. I've used your biochar. I've I'm working on getting more into biochar. But the first year we did biochar, we didn't grind it up enough and we blew pumps. So this year we're getting it a little bit better down. And
so you soak it in the tea bag.
Soak it in the tea bag.
And that way only the fine stuff gets into the
Exactly. And then you can use that tea bag to put wherever, re-inoculate compost piles, re-inoculate anything. It'll help break it down. You can go bury that biochar around your yard, and that'll get the longevity of the biochar rather than just spreading it straight on the ground. You'll get many, many more years out of it. But the slurry type biochar is also very, very effective. That's what I'm trying to get into.
So this is how we get the biochar to the hard to reach places like living roofs. We can do a topical application just using a fire hose. This is fire hose horticulture. Different ways to make it. I'm not going to spend a lot of time on this, but essentially the number of different kilns have been developed in recent years. Top-down, top-lit, updraft stoves, retorts, woks, pits. The latest thing that most people are enthused about is called the flame cap kiln or flame curtain kiln. I'll show a couple of those. This is a wok design that was developed in Japan, and the idea is that you have the stuff baking in the bottom. Your biomass is baking in the bottom. The flame is kept on the top of the wok. And because of that, no oxygen can get down. And so most of what's in there is going to just char. And when this top begins to ash, when it starts to turn white, you add more material and keep the flame up. And then when you don't have any more material to add, you're full, you quench it. You may lose a little bit on the top to ash or to water, but then most of what you have there is going to be baked solid into good charcoal. The other way to do that is a kiln that's shaped to whatever the dimensions of the wood or biomass that you're burning. If you're burning cuttings from prunings, you might want to have a long skinny one or a large wide one, depending on what you're pruning. You might want to have, for bamboo, you have maybe a 3 meter or 2 meter length one that you're using. And then you follow the same technique. It's a top lit burn, and there's no smoke. The only downside on this particular design is that you're losing the heat energy, the caloric energy. But in fact, that's only less than a fraction of 1% of the energy that's in the photosynthetic process that makes the hard carbon that you're left with. And you're capturing about 50% of the carbon that otherwise would wind up in the atmosphere. So one of the ways that this has been developed, the Hozu Farming Co-op started in 2005. This is in Japan, and they had about 150 hectares in the co-op that was farmland, and they were having difficulties for a variety of reasons. One reason was the aging population in the farm belt, and they had young people leaving to go work in the cities, very elderly people left with running the farms, and they would have what used to be called the satoyama, the second nature, the areas of commons that were on the hillsides that all the farmers had used. They would plant bamboo there, they would hunt for mushrooms there, And when the young people were gone, that went into a hodgepodge of broken down bamboo and so on. And what happened was the wild boars came and inhabited that jungle, and then they would ravage the rice fields. And if you're a farmer with 3 rice paddies and one of them gets destroyed by hogs, you've lost a third of your income. So they've had to go and come up with some ideas of helping the farmers. And one way they came up with was, let's use that bamboo and make biochar. We'll put the biochar as a fertilizer mixed with manures on the fields for making cabbages and other kinds of things. And then we'll market that together as the co-op in the stores as cool foods, because it's cooling the climate. The biochar being used in this way is taking carbon and sequestering it. So you're cooling the climate. So they branded it as cool veg, actually cool slaw. They were making cool slaw mixes for their cabbages. And they sold out. They were enormously popular, even though they sold it at a slight premium. And from that, they learned that there is this notion that there's a popular demand, at least in Japan, for things that help with the climate crisis. Which brings us around to understanding about the role of fashion and how things change in culture and how we as a human tribe signal to each other. That's really what fashion is about. We're signaling to other people, I am you. You are like me, I am like you. We are tribe together. That's what fashion does. And so can we use that to change cultural memes, change cultural norms? And the idea of branding things as cool rather than using words like carbon minus or carbon negative or decarbonization, which are bad neurolinguistic programming to begin with, using things like cool as a descriptor seems to me to be a very promising new way. Here's an example of framing. Now this is a product that reduces cow flatulence and methane by about 35%. Notice it's framed as a delectable solution. Biochar is fed to the cattle in delectable feeds, and it improves their digestion and their weight gain, and it reduces the need for antibiotics. The meat and the milk they produce is more nutrient dense and also delectable. So they framed this now, instead of talking about cow farts, they're framing it as delectable food, right? So mixing biochar at 1% by volume to silage prevents the formation of mycotoxins. It binds pesticides. It suppresses the formation of butyric acid, meaning that the fermentation can take place in a perfectly clean manner. It improves the feed quality. And then via the silage that's fed to the animals, the biochar finds its way into the gut of the animal, improving animal digestion, increasing roughage, and reducing greenhouse gas production. If you mix biochar with the litter in the floor of the barn, chicken coop, horse barn, cattle barn, goat shed, not only are you improving or reducing the putrefaction there, but you're improving the hygiene in the stables. It scavenges nitrogen. Remember the cation exchange effect of the pores. It scavenges nitrogen, and so that means ammonium can't form. So the ammonium smell goes away. If you've got a gray water problem somewhere nearby and you smell that ammonium smell, throw some biochar there. It'll take that ammonium smell right away. It'll scavenge the nitrogen. So there's a noticeable change after adding this to the litter of a goat barn of how they smell after a few days. You can use it as media to improve tree health and survival rates in nurseries and in tree plantings. You can use it to help revegetation, environmental remediation, tough farming and tough land. In fact, it does much better in poor soils than in rich soils. In rich soils, the improvements are minor. In poor soils, we're talking 400%, 800% increase in the first year from the immediate improvements in the soil microbiota. This is the largest CSA in Europe, Hartung, and he's serving about 20,000 subscribers. He's a Danish farmer. And he's now diversified into selling his biochar systems to other farmers. So he's got these greenhouses that are heated by a kiln that makes biochar, and he uses the kiln to make electricity while it's making the biochar, and it's using electricity for the fans and pumps and other lighting and whatnot in the farm, and then he's using the heat to keep his greenhouses going in Denmark all year round. This is another one I could show you, which is the BioLite stove. All right, this one is a little camp stove that you can take with you if you're going camping, and it's a double vault burner. It's got an interior container and outside container, and the gases, once you start the fire, it starts with a yellow flame and a little bit of smoke, and then pretty soon the gases are coming out through the vents at the bottom and traveling around. They have nowhere to go, so they cross the flame at the top on the way back out, and they ignite. And so then you get a gas fire, and you see the gas burner at the top, these blue flames coming in from all sides of the gases burning. That cuts off the oxygen supply to the area below, so the yellow flames stop, the smoke stops, and now you've got a clean burning gas stove, and it'll run for 30 minutes or more, and you can keep adding if you want it to run longer, but that's enough to do Knorr soup mix or spaghetti for your camping dinner or whatever you're making. But this one's got another feature. It's got a thermocouple that sticks into the center of the container there. So as it's cooking and as it's making its biochar from gas, it's charging up a capacitor. And there's a light on the side here that goes from red to yellow to green. And once it turns green, you can stick your USB port in there and charge your phone. So now you've got a way of charging your phone or your watch or whatever while you're camping, right? And while you're having your tea. And then you got biochar at the end of it. So you take the biochar, quench it, bury it in the ground where you were camping, and you've just had a carbon negative camping experience. So if it does all these great things, why is no one using it? And some of the reasons that people tell us, well, it's hard to find the right technology. You have to kind of be a backyard tinkerer. No, there are lots of these available, lots of different size and scale kilns that are available commercially now. Much of the climate discussion in policy circles revolves around untested, uneconomical geoengineering theories like BECCS or direct air capture, and yet here's a system that really does take carbon out of the atmosphere, and it's readily available off the shelf commercially there now. The other bugaboo is that there's not enough supply, and that if everybody started making biochar and making their energy that way, we'd wind up with geoengineered forests with genetically modified eucalyptus planted in plantations, some things. And there's really not a problem that way. There's plenty of biochar available in the market. You can buy it. These are statements by recent producers who have too much. This is a surplus of it. There's all these waste sources of biomass. You don't have to be talking about forests or plantations for making biochar. You can use sewage sludge. You can use livestock waste, chicken litter. You can use invasive species when you're clearing pastures. You can use slash from forests where they've had fires or they've had beetle kill. And just paper mill waste. There's enough paper mill waste just in Australia to handle all of the possible needs they would have to change over their energy system to biochar making gas pyrolysis. And that's Australia. Imagine what it would be in Canada where they actually have real paper mills. So there's plenty out there. The social inertia is the constraint. It's not the science. And what I've seen over the last 10 years, I wrote the biochar solution in 2010. And what I've seen now for this past decade is that we've been really pushing this idea of biochar as a super fertilizer and as a great way to change the chemistry of the atmosphere. And unfortunately, agriculture and forestry are some of the most conservative demographics out there. Farmers are not willing to change what they know works. And so even where you can demonstrate clear economic advantages sometimes, innovation is very slow. And so those are very large industries and it's tough nuts to crack. And even if you talk to the government agents and the people in the agencies or the secretaries in charge of these, the ministries of agriculture around the world, even if they're on board, they still say it's very slow to try and change these things. So what are we doing? We're starting to move biochar into new markets. We're looking at things that it could substitute for that are presently being done by fossil fuel-based or other resource extractions, such as combined heat and biofertilizer, as I mentioned with Hartung's farm or some of these others. But it can also be a water filter. And this is a serious need in many places. You have over-nitrified rivers causing dead zones in oceans and lakes and things. And why not start filtering that water and then take the biochar then, which has now been charged with all that nutrient, and use it as a fertilizer. I had a friend who was looking into this for tofu factories, taking the biochar as a way of filtering the gray water, keeping ammonia from forming from the whey that comes off of the tofu making process. And they realized that actually they shouldn't be selling the biochar to the tofu shops. They should be renting the biochar to the tofu shops and then taking it back to sell to farmers to use for fertilizer because it's got all that rich nutrients that come in from the whey. Biochar for building materials. This is another one of my favorites. We discovered that there's all these amazing effects when you mix biochar with clay plasters or clay paints. One of the effects is that it pulls mold spores out of the atmosphere, just like a charcoal filter on your cigarette. It pulls smoke out of the room. It's biobiology. It cleans the sick buildings. It cleans the air, and it does it relatively passively. It just exchanges from being on the wall surface. If it stops being very effective after a while, you just come back and do another painting. And it can take pollen, it can take mold. If you have hay fever problems, then you just paint your walls with biochar. And you can do all kinds of different tints. It doesn't have to be black. And it can be several layers deep, and it still can work if there's a breathable surface. And then building materials like living roofs, so surface material for living roofs. It can replace sand in non-renewables, and here's another one. This is a biochar cement cup. Okay, so I made this with biochar in the place of sand. Normally, when you're making cement, you have a certain part of it that's sand. So you just pass that around. One of the things you notice is how much lighter it is. It also floats. And sand is actually coming into short supply. The price of sand has been going up. Sand is not a renewable resource. And as you destroy the coral reefs, you get less of it. So what we're having now is peak sand. So we can think about having biochar as a replacement, and that has other benefits. It can replace toxic and harmful materials. I mentioned the animal antibiotics. This is a huge problem. Overprescription of antibiotics for animals creates superbugs. The antibiotic-resistant bugs that are now causing problems in hospitals and things, and it's the overprescription of antibiotics, particularly in the animal industry. So now we're talking about adding biochar to the diet. And what happens is improved digestion, improved immunity, resistance to disease, reduction of the need for antibiotics. It's the same kind of prophylaxis approach to feed that you would do with prophylaxis antibiotics, but instead of having to overprescribe and constantly administer whether they need them or not, you can just come in if they really need them. And so this is huge. Also, these microbeads, this is kind of funny. I don't know how many people see these, but every now and then there's these new products introduced to the market, like toothpaste that has plastic microbeads to form a better abrasive surface when you're brushing your teeth. So where does it go? Down the drain. Where does that go? To the ocean. Where does that go? Into the gut of the pelican or the dolphin or whatever else is in the ocean. Yeah, salmon. So do we really want to be doing our teeth that way? Now, I'm not going to say that biochar per se should be a good toothpaste, but maybe.
Glitter is another one, isn't it?
Huh?
Glitter.
Glitter, yeah. So acknowledging here the work of Hans-Peter Schmidt in the Ithaca Institute in Switzerland, looking at the way we can cascade the uses of biochar, the same product coming out of this one-time kiln, having made its electricity, can now be used to do water treatment. Then you recover that filter, put it into your silage conditioner, so it's improving the ferment in the silo. And now you take it and feed it to the animals, and you get as a digestif. It improves their digestion. And then it becomes manure, where it goes as a litter amendment on the floor of the barn and makes the barn smell sweeter. And then you rake that all up and compost it, and it becomes a soil amendment, which is your carbon sequestration and your fertility. All the same product, just cascading it through these processes. That was in 2010 to 2015. We were developing that model. And today, last year, we were looking at this from a permaculture standpoint of all the different products that you could cascade. And so now we think in terms of, okay, it's 2017, let's extend the cascade. Right now, on average, there's about 100 peer-reviewed journal articles on biochar every month. Every university that has an agricultural department has a research program. There are new journals coming out specifically devoted just to biochar. It's entering the field of electromagnetics and chemical journals and these other applications like concrete and buildings and so forth, not just agricultural journals. One of the things I'm always concerned about as a permaculturist is the ethics of production, and this goes into the characterization and categorization of biochar as a product. It should come from waste, ideally. I can understand it in some cases where you're doing a biomass crop, but you'd want to extract the other value of the biomass. If it has value as a leaf protein or as a feedstock, then you should, as a feed for animals, you'd want to do that too, and then take the waste from that, the resulting biomass, and use that to make your biochar. The methods I showed you of the kilns where you had the wok and the outside pit and those flame cap curtains, those are not capturing the heat. Ideally, the best of all worlds, you'd want to use that too. You'd want to find a way to have a clean process that uses all the heat. And then carbon sequestration. You want to have it as fine-tuned as possible to catch as much of the carbon as possible. And you want it to be ecologically beneficial, so the whole process itself should be done in a way that's not causing other problems. And social equity. You know, it's an opportunity for enterprise. It's an opportunity for all these co-products that can spin off of a single product. First takeaway, if we could produce and hold enough biochar either in soil or in semi-permanent structures as a paint or a plaster or some other way. We could conceivably return to the atmosphere, we return it to pre-industrial carbon concentrations. And we could do it in a matter of decades. We've run the numbers. It's conceivable. This process carries very few risks. It provides numerous benefits and can be made to self-finance itself because of all the possible products and services that you can provide. The intended markets, as we looked at this some years back and started coming to the present, were all of these industrial applications for waste management and agriculture and municipal waste water treatment and forestry and so on. Largely, those have not materialized. They're very slow to come into this field. What we've seen instead is the usual cultural creatives, the thought leaders, the permaculturists and landscape architects, transition towns, eco-communities, ecological restorationists. These are the early adopters. Question I have, though, is given what we saw of the climate charts, do we really have time for the slow process of adoption that we've been witnessing? Last month at the farm, we did a workshop on biochar from the ground up, where we started looking at a different approach. Let's set aside agriculture for the moment and think about other ways that we might be able to get biochar into much larger production. How about cool building? So if we look at what are the concrete properties and aggregate properties for biochar, how would they compare with existing structural materials? And as we look at composites, we can think about plastics, we can think about recycled materials of various kinds. How can we combine those with biochar, and what happens if we add in biochar to ceramics or asphalt or some of these other things? We find that biochar is lighter as we're passing around that piece of concrete. You notice that. It's got really good compressive strength, actually better than normal cement. It's got good flexural strength. It cures faster. And it actually absorbs carbon dioxide and nitrous oxide out of the atmosphere as it cures. It has electromagnetic shielding. I'll talk more about that in a minute. It's fire resistant, has good insulation properties and humidity control. Well, concrete's a big business, 25 billion tons a year. What if you replace all the sand with biochar? You're talking, if you just got a 1% market penetration there, that's 250 million tons a year, which would be 205 to 245 megatons of carbon sequestered annually, which is huge. If you talk about the properties, why you'd want to use it, it's got physical properties that are favorable and the hydroscopic properties that are favorable. It's got good absorption of existing greenhouse gases. As it cures, the building itself begins to sponge up outside air and greenhouse gases. It has good fracture properties. It's less likely to split and fracture over time than concrete is. So if you build a bridge or a roadway or something like that, it's going to last longer. It's less likely to fracture in an earthquake. Crack contouring, this is a way of determining how cracks propagate. It's more likely to be arrested quickly because of the biochar features. Radiative shielding is a really interesting one. Okay, so I've got this meter here. It's a tri-field strength meter, and it checks out electromagnetic fields. And I made a piece of paper that had biochar in the paper. And I put the paper between this meter and the electric outlets on the wall, and it dropped the meter to zero. One thin piece of paper dropped the meter to zero. It shields electromagnetic fields. Now, if you've got bad Wi-Fi reception and you want to get better Wi-Fi reception in your rooms, you probably don't want biochar in your walls. But if you're trying to block Wi-Fi signals or electromagnetic signals of any kind, this putting biochar in a paper insulation or in a plaster or in a paint is a way to give yourself electromagnetic shielding. I've actually thought, that's not a bad idea. I'm going to make a little paper pocket protector for when I'm carrying my phone so that I don't have my phone next to my heart all the time with electromagnetic field around it. I will protect my heart with a piece of biochar paper behind. Anybody could do it. It's easy. Those kind of properties, who knew? There's a test being done now by the Rensselaer Institute of Technology in New York, where they're making these tiles for roofing with biochar. And they're mixing concrete and biochar. It's lighter, so it's easier to get up on the roof and install. It seems to hold up really well. It's waterproof and easy to make. Okay, what about adding it to roads? So they started looking at making biochar from switchgrass and adding it to asphalt mixes, and what would be the difference in normal wear and tear and things like that. Another huge market, talking 1.6 billion tons per year. If you had a 10% penetration with biochar, that'd be 160 million tons, or about 89 megaton carbon sequestration annually, just from road construction. So it would be huge, and as they looked at it, they found that it actually had improved qualities of tire life and so forth. So it was actually good, it lasted longer, cracked less, could absorb frost heaves and so forth. Biocomposites is looking at combining biochar with wood and plastics, okay? So I'll pass this around. This is a bunch of polystyrene coffee cups and eggshell cartons and take-out clamshell containers, all made of polystyrene. Typically they wind up in the ocean. And we melted them down with acetone, stirred in biochar, and formed this little nugget here. Now I didn't bring it because it's difficult to take through customs, but I could make those in any shape. I could make those like a shingle. I could make those like a suitcase. I could make them as a kiteboard or a surfboard. I could do any number of shapes for that, and it's very lightweight. It's as hard as steel. You can't break it. It's very difficult to saw. And it's a new biocomposite made of biochar. So it's a reuse of a common polluting plastic that is now sequestering carbon. Adding little biochar to almost anything helps sequester. And again, we get back to the problem is not science or technology. The problem is people. We have to think about how do ideas spread? How do we get people to adopt new ideas? And Paul Hawken has done a great service in showing us all these different ideas for drawdown, how you can draw carbon out of the atmosphere, how we can start to address the legacy carbon problem up there. And it's, again, not a technology problem. It's an adoption problem. It's getting people to start doing the things that they need to do. And there are hundreds of these ways that we could start doing. It's not all about biochar, but we could be taking, biochar alone could take out maybe 10 gigatons of carbon per year if it were scaled. Reforestation of available degraded lands could take 5 times that. Kelp farms in the ocean would help rebuild fish stocks, absorb carbon, make food and fuel. That would be a huge benefit. Eco-villages and B corporations, they offer carrier media to speed deployment of these things, showing how these things are done and showing ways that they improve lives. In fact, they improve lives so much that you start to tick off the Sustainable Development Goals of the United Nations. You can start ticking off all 17 of those by the improvements that come from following these drawdown techniques. That's really the way you set your goals. So getting to scale. At present, the world subsidizes fossil fuels at the rate of $500 billion per year. Not too much different in euros. That's about 12 to 15 euros per ton of carbon dioxide. So around, and that's being paid to the fossil fuel companies to do that. So around 200 billion metric tons of carbon dioxide have accumulated in the atmosphere since the beginning of the Industrial Revolution. That's 200 gigatons. And that raises concentrations by more than 100 parts per million. We started at around 280, we're now around 410. And so if you took those marginal or unproductive lands that are going slowly back to trees or into desert and reclaim them using biofertilizers and tree planting and all these other good techniques, holistic management, rotational mob grazing, water management, key lining. If you used all those good techniques, you've got about 4.8 gigahectares currently available for that. And if you were to go at the rate of 200 megahectares a year, you could bring us back to below 300 parts per million in about 40 years. That's the math. So we could get back in the lifetime of those now around if we applied ourselves. We could do it using these techniques. But that's the scale required, and that's daunting. What is 200 million hectares a year? It's 4 Spains per year. To do that much tree planting and biochar making, probably about 100 million people. So how are you going to pay for 4 Spains a year and 100 million workers? How are you going to do that? And my concept is to use microenterprise that comes from those same processes, that it actually is a income generator. It's a profit generator. You have to look at the bigger picture and how things work together. And Malcolm Gladwell some years ago wrote a book called The Tipping Point. He said, you get leverage points that ideas spread like viruses, and they follow certain rules. And one rule is the law of the few. It doesn't take a majority to decide. A small number of people change things. They're the thought leaders, the cultural creatives, the social mavens. The second concept is stickiness. An idea has to be delectable. It has to be sticky. It has to hang with you and seem to you to be, that's neat. That's a good idea. I like that. And then the third thing is the importance of context. Well, the context in this case is climate change. We've got plenty of context. We're facing an existential threat. In permaculture, we talk about social permaculture, which is the idea that personal relationships are capable of design. That we actually build relationships among plants, we build relationships between plants and trees and water systems and houses and everything. We also build relationships between people and groups of people. And so thinking about how can we have a built environment that improves the lives of people, and we have designed in greater biodiversity, drawing carbon from the atmosphere, cleaning the water, doing all these other things. It's actually a design challenge, but it's not that difficult. And there are lots of people taking permaculture courses and doing this sort of thing in the world. Eco-villages, for me, have been the medium by which we can make these transformations happen. Why? Because they're the carrot. They're the proof of concept that life can be good while you don't have to, sacrifice and wear a hair shirt and do without this and do without that. You can have a really good life in a new paradigm. So that's the concept of eco-village, and eco-village transferring as cities being collections of villages. So eco-city. or regions, where you have eco-regions and eco-districts. You have transition towns that gradually transition existing habitats into eco-villages. And eco-villages come with a suite of tools. These are all the kinds of things that we learn how to use to make these social transformations. Well, that was the model for this experiment that happened in Tennessee a few years ago. Mantria was the name of the company, and it went out to make the Carbon Fields Eco-Village project in the Sequatchie Valley. And the idea was to produce heat and power from a biochar production facility using the woody wastes from the surrounding forest industry. And the forest industry was paying tipping fees. They were paying to ship the waste into Alabama to be disposed of. So this company could collect the tipping fees, make the biochar, produce the power for all the houses, and then also begin to use the biofertilizer and sell that and so forth. They started planting large acreage of bamboo and miscanthus to feed the process also. Imagine cool Jordan. Imagine where you have currently the government of Ireland is offering biomass energy grants. Imagine you got a grant for upgrading the steam plant to a pyrolyzing, gasifying, biochar producing, electricity co-producing heat plant. So you get your district heat, but you also get electricity, you get biochar, and you're going carbon negative, which is bad. Programming, let's instead say cool. It's cool. You actually get a 30% fuel efficiency gain too. Some of this idea is not new. It was the Sarvodaya movement in Sri Lanka, which came out of a follower of Mahatma Gandhi named Aryadhyatna, who returned to Sri Lanka from India in the 50s. And he started this self-help movement there, where each village that got itself up to meeting the basic requirements for happiness, human satisfaction, human capabilities for food and water and all the basic necessities, had an obligation to adopt another village and help that village reach the same. So it was a pay-it-forward scheme. And now there are 19 or 20,000 villages in Sri Lanka that are part of Sarvodaya. And more than 2 million who call themselves eco-villagers there. But this is the idea of social well-being integrally tied to this process of change. You're holding that out as something that you benefit from rather than something you're being punished or pushed into by regulation. My idea was the cool lab. So we would take a facility that had a source of woody wastes or biomass and turn that into electricity and biochar. But also we could look at the feedstocks. Okay, so if we're producing some woody matter like, say, moringa, you can get the leaf protein and extract that first. And then you have the bagasse, the leftover leaves, and that can become biochar. You have the bamboo that can be used for various different products at a premium grade, and then the lesser grades can be used for making biochar. You have these different micro enterprises that can all be put onto this cool lab as add-ons, and it can be totally self-driven. You could have semi-autonomous, independent enterprises that are all networked together and maybe marketing together under the cool brand. But this is a stimulant for regenerative design at the village scale. And we begin to tick off the sustainable development goals that this can hit. Equalizing income share, opportunities for women smallholders, opportunities for minority groups, different ways of ticking off through some of these sustainable development goals. The other thing that would be really helpful in this is the B Corporation concept, the idea of social enterprise with a social goal. So each of these new micro enterprises could be a B corporation, and they could be linked together into a B network so that you would have ways of mutual self-aid, and you would have these micro-enterprise hubs. That's the basic schematic of the process, and this is an example of one that was done in Hawaii a few years ago, a Hawaiian mahogany farm. These were proofs of concept. These showed that it could be done. This is all, they were making, the mahogany farm was taking the nurse trees out, turning that into biochar, in the process using the heat to make ice. The ice was then sold to the fishing fleet for the fishermen to keep the fish on ice. And then they also used the horse manure to mix with the biochar to make biofertilizers, which they sold. And they had all these products coming off the mahogany farm. Okay, so I'm currently working as a permaculture designer at the eco-village scale and designing now what we're calling ecool villages, carbon drawdown villages. One of the ones I was called to work on is in Mexico. This is Cancun Airport as the top of the picture. Farther down, you got the city of Tulum. It's an old city with Mayan ruins. And within that, there's a beach zone, and there's this large project of about 240 hectare, which is almost half the size of the original city of Tulum. So taking a look at this 240 hectare property, who are the clients? Who are the eventual stakeholders? Well, they're thinking about having visitors kind of like eco-tourists and maybe some rock concerts, and there's a Rajneesh ashram, and there's yoga studios that want to go in there, and they, you know, it's the hippie Tulum Mayan Riviera crowd, glampers and Burning Man people and all that sort of thing. So that's their stakeholders. What it looks like today is this. That's my client. So I look at how can I protect that from who's actually wanting to pay me. And you know, this is what they're working with. And they have this nice beach, good kite surfing, and they're going to turn this into an eco-village, they say. Okay, interesting concept. Some challenges. One challenge is, if you look at the side view, you've got this unusual hydrology there on the coast, where the fresh water comes from underground rivers, passes with cenotes that are open to the sky, and then you have the steep slope down to the beach. You have hurricanes that come about every 8 years on average, so anything built on the beach is at hazard, and you have the gradual erosion of the beach due to sea level rise. So these are challenges. One challenge is fresh water. You want to protect the fresh water. It's a resource. It's what all the wildlife there depends upon. So nothing can go into that fresh water. It has to be kept sacred. You've got a nice resource in terms of what you can do with bamboo. So if you wanted to have a light footprint and build sort of eco-lodges and glamping for these visitors, that's conceivable. If you kept it light and light touch, close to nature, building into the natural environment. The question that I had, and which they had, which was, what do you do with their sewage? What do you do with their gray water? Because you have that many visitors, you're going to have some of that. What are you going to do with that? So I came up with this idea of a redesign of the Mayan pyramid. In Romania, they've been experimenting with these sewage treatment pyramids for military bases that are essentially John Todd's living machine done in a giant Romanian pyramid. And the sewage is pumped to the top, and then it flows through different stages. It goes through reed beds and lagoons and various different arrangements of living things until it gets perfectly purified and cascaded through waterfalls and goes out the bottom as clean water. I said, okay, and actually they harvest off on a daily basis. They harvest off all the biomass that comes from that. I thought, well, that's neat. Now you've got that biomass coming off, biochar, electricity, all the things we can cascade off of those things, including leaf protein. So this is my design for the Mayan pyramid, that you would come to this place and you would see this, there would be one of these Jürgen Kleinswasser sun pulse engines at the top that pumps the sewage to the top, and then it would cascade by gravity all the way through. and then come out as clean on the bottom. Within the landscape of the area, you'd have this Mayan pyramid. This would be one of the things you see as you're sailing along the coast. You would see these pyramids. And people could live very much in these bamboo structures in the forest and along the water systems, very light touch, open to the sky and the air and so forth. So the idea there is to take back the climate with cool villages. Next project we're working on is called El Valle. Yeah, I'm on track. I'll be done in just a few minutes. El Valle, which is in Dominican Republic, and this is the a valley that was fairly remote, but now they've opened it up with a new bridge over a river that means that the developers are likely to come in. The village people are my client. They want to protect and preserve the pristine nature of the valley. So we looked at who are all the landowners. We went and did some of these surveys and figured out who are all the landowners and can we get them into an eco-covenant so that we can declare it an eco-district and we can have some sort of common shared understanding of values. We had all these town meetings and we got everybody on the same page. We said, look, you can have two different kinds of development here. In one kind of development, they build high hotels on the beach and you get to work as maids and gardeners and things like that, you have automobiles. In the other form of development, they come in as bird watchers and kayakers and kite surfers, and they live in very rustic bamboo habitats, or maybe they just come in for the day, and you're tour guides, and you're fishermen still, and you're farmers still, and you work your own hours. Which would you prefer? And to the man, everybody said, we would much prefer the way we live today as fishermen and farmers. And we want to keep that. That's our lifestyle. Okay, so we brought in all these different players to help with the design. We got the government on board, and they've declared it a natural and historic preserve. They set aside offsets. We're up to 30,000 hectares now of national preserve offsets. We've done the satellite imaging and profiles of it. We know where the underground water systems are. We know where the erosion capabilities are on the hillsides, and the wildfires are most likely. And we've done the master planning now for light touch development of farming and fishing and so forth in the Village Valley, and a little bit of there for the school, because as we had these town meetings, we had to ask, well, what is it you want? We want better schools for our kids. We want health care. We want a clinic. We want this. We want that. Okay, so let's figure out how to do that. We brought in the green school. We brought in Elora Hardy to look at the possibility of building a green school there. Can we have some sort of ecotourism that would go with that? We also looked at environmental business opportunities if we started to do this cool lab. We could have leaf protein, and we started to plant out moringa, coconut, papaya, lots of other things that could provide food and then leaf protein and then biochar and then water filtration and all these other things. So the cool lab has actually been penciled out. It's potentially very profitable. There's a high return on investment. We can start selling packages to investors now. One of the things we did there was to crowdsource the development budget. How do you do that? Well, we looked at, we've got these offerings that we could make to people who want to come in for tourists or second home sites or place in a very nice area to live, have a second house, a retreat center, yoga center, whatever you want, at this place we're calling the Gathering Place. And we've planned all that out. We said, well, how about if we offer people a cabin? You could build and own a cabin there. There would be a common eco-lodge for food and social events. We'd help you with the organic and sustainable materials for this, mostly bamboo. Cost is about $30,000. But what we'll do is we'll rent the cabin while you're gone to students at the school and to visiting lecturers and things like that. And we'll use that rental. We'll pay you most of that. And so we reckoned it would be about 9 years that you would pay off that $30,000 investment. It's not like a timeshare where you pay a maintenance fee. It's where you own it and you get back money for renting it back. So you'd have a couple months of the high season where you might want to come in and do it, be there. The rest of the time you'd be getting about a certain amount per month in rent. Second takeaway is that our take, make, waste economy has led to all these countless calamities. And cool design provides a possible way, a possibly profitable way out, and to build a new thriving economy where there's no such thing as waste. I'll mention one other example, which is the ecological restoration camps. This is John Liu's idea for employing disempowered youth around the world at places that they could be rebuilding the ecosystems. Right now, the first prototype camp is going in Spain, and the first people are right there right now planting trees and vegetables and stuff as we speak, and they are regreening the desert in that part of Spain, turning back climate change in that part of Spain. They want to put those everywhere. This is where we can start to train up those 100 million people. We need to plant all those trees all over the world. In October 2016, we brought it all together at the invitation of Secretary General of the Commonwealth. This was drawdown, permaculture, ecosystem regeneration camps, eco-villages, cool design. We all met in London at this meeting held by Patricia Scotland. And for a couple days, we came up with a path forward. We set out some pilot projects to show the proof of concept. One of the ones we've developed is this one in Belize, which is a Commonwealth country, where a small Mayan village, San Pedro, Colombia, wants to build a cool lab and show how it's done. And we have more than 100 permaculture design certificate holders living in that district right now in Belize. And we could put that plan into motion. It just needs the finances, which is what the Commonwealth is working on. And that project ticks off all of the 17 Sustainable Development Goals and more than 20 of the drawdown techniques. And it's using this basic circular economy of there's no such thing as waste. Closing the carbon cycle. So, final takeaways. This is already a revolution. It has to be ethically grounded or it will be destroyed. We are not too late yet, but this could be our only chance. I'm asking anybody who wants to get involved to go ahead and join us. I'm recruiting here. We have second home sites in El Valle and eco-villages forming in Mexico and volunteers needed on the ground in Spain and at the ecosystem regeneration camp and in Belize. We've set up 2 organizations brand new now. One's called the Cloudburst Foundation, which is to put all these people together. It's the Foundation for Collaboration. And the other one's called Project NOAA, or NOAA Regen, which is the idea of a $1 trillion investment fund that would put a portfolio of these projects, shovel-ready projects together and draw in investors. So there are those who say it's already too late, that humans have had their chance, that we blew it, welcome to the apocalypse. And I would say, put away the sandwich boards, the end is not yet nigh. And I'm going to show you my film here of what we're doing to introduce people